Okay, so the next stage of the class is analyzing work and energy. Let's see. This is part 2. So this is work energy kinetics. Take that into, work and energy is a new type of analysis to analyze the kinetics of a system. Kinetics, remember, is now related to the forces that cause motion. The motion itself was kinematics. We spent a long time on talking about the different types of analysis techniques for just the motion itself to describe the motion. And now we're relating that to the forces that cause it. And we spend a lot of time directly talking about the forces that cause motion and how we can analyze systems. But oftentimes we can get to final results a bit quicker if we bring into the new ideas of work and energy. Okay, and this is part 2 that extends that force mass acceleration analysis we've been doing more recently in the different coordinate systems: Cartesian, natural coordinate systems, and then the polar or cylindrical coordinates. Okay, so what we're going to do is this is going to take 3 different lectures, where the last one will be reserved for examples, and that's where all the examples will be. This will be a short one, introducing us to the main ideas of work and kinetic energy. There's no coincidence here, right? The fact that we're talking kinetics and we define something called kinetic energy related to motion, the energy associated with motion, because forces cause motion, right? And then the next one is also going to be on the theory, but that's going to be a little bit more bulky, talking about the other types of energy and what work does to a system that has more energy involved. So think of this as the introduction, more straightforward version of work kinetic energy. We'll have the bulk of it in the middle lecture, and then the last one will have the examples. Okay? So let's see here. Let's draw a path, as we've done many times. This is the path of a particle. Okay, yep, and let's see. Let's put in here a origin of some coordinate system, however we choose to do it. And then we would have a position vector to a point. Okay, so let's say this is R, and we'll call it 1 because it's at a particular time. So S1 is its distance along this from some 0 point in our S coordinate. And so this is going to be governed by the path as a function of time. So position with time in terms of coordinate, along the path direction is S. At a particular time, we get to this location defined by this position vector. Okay, so then later on, we could have a different position. And let's actually purposely put it like there-ish. Okay. And one thing I'm going to do here, which is why I'm going to take this nice and at what I consider an appropriate pace here, is let's do things actually right in terms of how the calculus works itself out here. Okay. So this is R2. That's going to be related to R1. Oh, I did that wrong, right? This is where I already made the mistake. S2, this position, this coordinate along the path, this is going to be a delta t time later. Okay, so you see I don't subscript this with anything. This is really the S coordinate at a particular time, and then a delta t time later, t plus delta t, is going to give us to the second position, right? So then that means that R2 is going to be R1 plus some change in R. Okay, well, what is that change in R? Right, well, that's going to be just from vector addition there. This is delta R, and that's why I wanted to put a little bit along the curve. So what we haven't done is we haven't zoomed in enough to say that this is an infinitesimal change. Okay, let's see here. We could put a coordinate system onto this, and I think the most natural choice would be the natural coordinate system. So we will put our tangential component there and our normal component there. Right? Normal doesn't care about this origin to a coordinate system. Maybe if this was a Cartesian coordinate system or whatever, right? Because there is no really origin when we have this coordinate system. We're just kind of compare the different coordinate systems. And then, by the way, that this arc length here from there to there is delta S. All right, so that's following the blue curve to get from R1 to R2, or S1 to S2, we should say. Okay. So that's fine. These are all deltas, meaning these are differential quantities. This is a differential time. It's a finite value, 0.1 second later, and this is a position vector. Well, it's a change in a position vector. So, but it is a vector, and it has it's a difference, right? Different in these 2 points. Okay. So now to get to actually the infinitesimal relationships, right? So the the differential relations and these differences here, right? The difference in time, the difference in the position, to get actually differential relations where we go to infinitesimal time. That is where we have to drive these deltas down to 0 as low as possible, right? And so that it's an infinitesimal change. To do this, we'll zoom in sufficiently close first, such that the path is well described by a linear function, or a linear, it looks like a line essentially, such that the path is approximately linear. Okay, that'll help us how to draw the picture, but better yet, what we're actually doing mathematically, we're going to let this delta t, the change in time from when the particle is there to the particle is later on, we're going to drive that to 0. All right, take the limit as that goes to 0. And as we do that, delta r also kind of heads to 0, although in a vector sense, and delta s becomes 0, right? But how that happens, right? How much does the s, how does it approach 0 as delta t approaches 0? That's a calculus idea, right? So the way we represent this is really done on the figure by representing delta t, delta r, delta s, these quantities as infinitesimal, so arbitrarily small differentials, dt, dr, and ds. So the point is that we're driving them all to 0, but if we ever have a question about, well, what is the rate of delta s to delta t as they drop to 0, then we have to write them as differentials and they become derivatives. So, okay, let's do all of this in once here by zooming in far to, so what we're actually doing here is bringing this r2, so delta r gets smaller and smaller as our time gets smaller and smaller. And if we zoom in, make that small enough, arbitrarily small, no matter how this is drawn, it'll look linear and some close approximation. Okay. So let's see. So we do this. Our path is going to look pretty much linear, like a straight line. Here is S1 with the R1. And instead of just R1, let's just call that R, so that this other location is R plus delta R, or plus dr, right? A differential, arbitrarily small, infinitesimally small, whatever you want to say, right? So then this is S1 of t, S1 equals S of t, S2 equals S of t plus infinitesimally small dt, okay? It's always important to say what is the process in which we are driving the system toward a continuous change, right? And here the key figure is we've zoomed in far enough so that there's no more curvature, okay? So then this is dr, and do you see how now that is perfectly, right, through vector addition, that is perfectly, or the magnitude of dr is ds. That's the key, right? So we don't need to make any approximation that delta s is pretty close to what the magnitude of delta r is, all right? And so this procedure is full. All right, and then again, if we put a coordinate system on there, that doesn't change here, right? This is still ET and EN. Okay. Okay, so a few maybe observations, few things to note here. dr is tangent to the path, where it wasn't up here, right? Delta r was not necessarily tangent to the path. When we, in this driving to zero process, zooming in far, we can make that claim. So that is, this is along the tangential coordinate. So dr as a vector is the ds, small infinitesimal change in the arc length, and that's the magnitude, and then its direction is along ET. Great. Okay, let's do another note here. Well, let's first actually do something important, right? This is now going to get us to the energy of the system. We're going to take Newton's second law and dot it. So Newton's second law, and that's a vector equation, so we can dot it with this dr vector. Okay, so what we have is sum of the forces equals, I'm going to leave a lot of space there, mass times acceleration, but I'm going to dot this with the dr vector, dot that with the dr vector. Remember, that like projects a force into the dr direction, so that's the direction of motion. All right, we're going to project an applied force. If there is an applied force somewhere on the particle between here and here, we're going to project that into the dr, so the direction of motion, and we're going to get the component of force that's along the direction of motion. All right, and then there's something going on with the magnitude here too, right? So maybe this is important to note now. That Newton's second law, I put an arrow over the top of it. I'm just kind of representing that it's a vector relationship. It's a vector equation, but now that we've dotted it with another vector, we have a scalar equation. There is no more, when you dot two vectors together, there's no more direction. It's just going to be a single number, right? Okay, so let's take this component by component here. Well, it's not component by component. Let's do the dot product, right? What we have is sum of forces in the tangential component, E of t, plus sum of forces in the normal direction, E of n. That is the sum of the forces there as a vector, dotted into ds et, and then that equals mass acceleration in the tangential, so tangential acceleration times the tangential unit vector, plus normal acceleration times the normal unit vector. That is dotted into ds et. Okay, great. So now we need to make some space here, because we have some work to do. That is a pun. Okay. Now this is another advantage of having the natural coordinate system, right? Since ET is perpendicular to EN, I guess this is true of any coordinate system, right? As long as a good coordinate system by design has it that their base unit vectors are perpendicular to one another. So ET dotted into EN is 0. That's true of any two vectors that are perpendicular, right? Also, when we dot ET into itself, and this is true of any unit vector, so it's also true for EN, that you're just getting the magnitude, which is just 1. Well, it's actually the magnitude squared, but that's also 1. Okay, so this statement is true for any unit vector. Okay. All right, so if we go back, oh gosh, can't even pick it up. If we go to here, right, we're going to have an ET dotted into ET, that'll be 1, and we have an EN dotted into ET, that'll be 0. So this does not contribute at all. And this is what I mean. We're just going to get the tangential component of the force. What's the tangential component? It's the component of the force that's along the motion direction. That's going to contribute to this equation. Anything normal to the direction of motion doesn't contribute to whatever equation we are deriving here. Okay? So sum of the forces in the tangential component direction times ds. And again, there's no vector anymore, right? The et dotted into et is just 1 as a scalar. That's going to equal mass times acceleration in the tangential direction times ds. And then again, that is just 1 when et dotted into et. En dotted into et is 0. All right, so this is it. Okay, and it's a scalar equation. Okay, we're getting there. We're getting close to getting an energy and a work showing up here. So recall, we got to do one thing here, which is that the acceleration in the tangential direction, by definition, no matter however curvilinear our system is dv dt, the change in the speed with time, right? The acceleration in the direction of motion is the change in the speed with time. All right, and then we do the chain rule trick, dv ds, ds dt, recognize that this is just velocity there, and we have v dv ds. All right, that should look familiar. We've done that a number of times, okay? So we're going to apply that. We're going to take that and apply it here. That'll go into there. And we will write the left-hand side in its original form just to have it more general. So when we write left-hand side in the original form and then apply this identity, right? Or, you know, mathematical principle, right? So this was the original form here, and then now we have this equaling mass times v dv ds. Okay, and the reason we're doing this is, well, this is now just a differential in terms of velocity. If we choose to then integrate this in, well, they're both differentials, so we could integrate this side from v1 to v2, because this integration variable is v. Integration variable here is actually r as a vector from r1 to r2. Right? We're going from one location space. Now we're kind of thinking back in a macro scale, going from some position 1 to some position 2. Right? From r1 position to r2 position. Right? Well, what is the other one's going to be? What's the velocity here? What's the velocity there? Or the speed? Those two locations. Right? This then equals, on this side, we have an mv, integrating that'll become v squared over 2, so 1/2 mv squared, and then we plug in the bounds, this will be v2 squared minus 1/2 mv1 squared. Okay, so the final form, right, the form that I'm going to choose to leave it at, which is general enough but also specific enough for us to do something with, as in terms of this methodology, is here. 1/2 m v2 squared minus 1/2 m v1 squared. Okay, so let's take just a few minutes here talking about what we see, and then we'll come back next time and do more with this. Okay, what this says, okay, what this left-hand side is, right? This is the net force on a particle net force on particle in the direction of motion. All right, we already broke this down and then I wrote it back, right? That dot product really means take the component of force in the direction of motion, in that tangential direction, and integrate it over the distance of travel. So the distance of travel from R1 to R2. And what is R1 and R2, right? That is, you know, a different time maybe, right, as the particles traveled, right? Well, what this is the work done on the particle, or to the particle. That's how we define what work is. Okay, so this is something like, this is the forces being applied over a distance is the work, right? This other side of the equation is, let's see, this is now change in kinetic energy. Change in kinetic energy, I will use KE going forward, because we're going to see it a lot, from position 1 to position 2. okay, where the kinetic energy at, well, of just some object of mass m with some speed v is 1/2 mv squared. Okay, and the units here are kilogram meter squared per second squared. Right, kilogram meter squared per second squared, that's the speed squared. That is a joule in SI units, or a Newton meter in SI, or foot-pounds in US. Okay. All right, so I think what we'll do is we'll leave it here, right? This is our introduction to work, and we got our first equation. Work applied to a particle changes its kinetic energy, right? Well, good. That's not the whole story, though, right? There are other forces. We're going to break up these forces. I mean, this is general, right? We have to sum up all the forces. We're going to break this up into, like, well, there's specific forces that we can treat differently than other forces. And yeah, that's going to be where we're going to do. We're going to talk about non-conservative and conservative forces. And that's going to be a bit of a lengthy lecture. The next lecture is going to be a bit lengthy one. And then we'll do examples. And the next one is going to be lengthy and focused on theory only. Okay? Because it needs it. We need to get comfortable with these concepts.